Hello friends and welcome back. In this lecture we'll be talking about angular momentum, sort of completing the arc of this journey of finding analogs for translational quantities to rotational quantities, so the description and the behavior of rotational motion and so forth. And up until now we've seen that basically for every important quantity such as position and velocity, acceleration and force, and so on, we found for translations, we found rotational equivalents or analogs that really have almost identical role in the rotation angle, the angular velocity omega, the angular acceleration alpha, and the torque tau, which, by the way, you may remember we defined as this weird-looking vector product between the lever arm and the applied force. Among the things that we discovered is that the good old Newton's second law has an equivalent for rotations, which is really, there's another one missing, which is mass with moment of inertia. The other analog that I want to write about, mass and moment of inertia. And we discussed, consequences of this, applications, and it was really nice and interesting. And you may have noticed that there's the conspicuous absence in, both sides here, of anything related to momentum. What happened to momentum? You may remember in Intro to Physics or in previous studies that this quantity momentum, defined as m times v, actually let's put a vector on top because it's a vector quantity, it's related very, very closely to a bunch of phenomena that are really important and interesting, particularly collisions. So when two objects hit one another, or actually more than two potentially, two explosions, and in particular you may remember that momentum is conserved, and that in a sense where isolated systems, where only internal forces act, the total momentum is then conserved. So what is does momentum, linear momentum, have an equivalent for rotations? And the answer is yes, a resounding yes. And the name of this equivalent quantity for rotations, for angular motion is, well, without a lot of fantasy, angular momentum. We call it L. And you may remember, actually, we defined this in week 2, in gravitation week, just in passing, as this cross product, let's rewrite this, or mr cross v. So I'm looking at a pivot point. As usual in rotations, we need to choose not only an object and its motion, but we need to also choose a reference point that we look at the situation from. So let's say that there's an object of mass m moving at velocity v. As seen from a pivot, the angular momentum of this object m is precisely this vector L, which is mr cross v. Right-hand rule. So in this case specifically that I'm looking at, the angular momentum would be pointing into the page, perpendicular to both the lever arm vector and the velocity vector. If, for example, just to draw it again, if this is r and the velocity of the object were directed like this, then instead it would be out of the page. Okay, all the usual stuff. Okay, so far just giving names and defining things, but let's see how this is important, okay? Clear the page, and let's go back to Newton's second law. So for translations, we wrote it as F equals ma, and we discover that if you add it to the definition of momentum as mv, what it turns out is that you actually find what the deepest and most sort of a general phrasing of Newton's second law for translations, which is that actually F is the net force, hey, net, not just any force, is equal to the rate of change of the momentum. So this generalizes F equals ma to situations where maybe the mass is changing and things like that. And so let's look at rotations. We saw that for rotations, the net torque is equal to the moment of inertia times the angular acceleration of the object. And now, equipped with this new definition of angular momentum that we defined as r times p, we get to actually, you can show that this is exactly equivalent to two things. One, that the Newton's second law for rotation, the most rigorous and general expression of it is this, that the net torque is equal to the rate of change of angular momentum. Let's write it here. Net torque is equal to the rate of change of angular momentum. And let's continue on the parallel. See, not only is this the right definition for L, but if you replace m with mass with moment of inertia for rotations, and if we replace v, velocity, with angular velocity, omega, and obviously replace momentum with angular momentum, it turns out that this is also equal to the moment of inertia times angular velocity. Wonderful. So these are the two key equations for this video. The concept of momentum or quantity of motion was for linear momentum. Quantity of rotation is for rotational motion. Is contained in the angular momentum, this quantity, which is defined as this cross product. And in practice, when you look at an object of inertia I spinning at angular velocity omega, this is precisely the combination that tells you the angular momentum of that object. How do you change angular momentum? By applying a torque. In the same way as how do you change the motion or the velocity of an object? By applying a force. So this is Newton's second law for rotations. Okay, very nice. Actually, since we're talking about changing, how to change the value of angular momentum, let's draw a precise, identical parallel to what we had in translations. You may remember that we had defined this notion of impulse. Which was, well, for a constant force, it was this force times the time that it is applied for. Or if we want to be extra precise, it will be some integral of f in dt. And we said that the net, this was the impulse momentum theorem, told us that the net impulse on an object was equal to the change in the momentum of this object. I don't know why my tablet does this. There you go. This was the impulse momentum theorem. Well, by now you know where this is going. We have the equivalent statement for rotations where we can define a rotational impulse let me write it down. Impulse, which is the torque multiplied by the time it is applied for, or as usual, the appropriate integral if you have a torque that is changing with time. And you can write the impulse momentum theorem for rotations, which reads that the net rotational impulse is equal, unsurprisingly, to the change in angular momentum. Okay. Again, we're literally simply replacing verbally, whenever we say linear impulse is equal to the change in linear momentum, the angular impulse or rotational impulse is equal to the change in angular momentum, right? So there's perfect analog between the roles of these objects, all right? So if anybody asks you, hey, how do you change angular momentum to something? And you say, well, by applying a torque, a non-zero torque, but even more importantly, the non-zero torque is a non-zero impulse, rotational impulse, okay? Nice. Okay, I think this is it for this video. Thank you very much for watching, and I'll see you soon.